Hello and welcome everyone to another episode of Nowhere Yodaris. This is your host, Mahmoud Nowhere. Today we'll be going through isomers. We're going to be going through organic chemistry's own isomers. We're going to identify what are the common isomers, and we're going to identify how to basically number them and how to figure out their configuration and differentiate between them. Alright, so shall we start? So isomers are basically there when you have one or two atoms connect in a structure, and they can maybe, I don't know, differ from another atom and different in terms of like structure or a physical properties or arrangement or configuration. So we're here to explore the types of isomers. We have constitutional or structural isomers, and these share the same molecular formula but different structures. So for instance here, um, we have this structure. You see how in the upper structure the fluorine is in the middle. It's the same molecular formula, same arrangement, except for the fluorine. And then here the fluorine replaces the hydrogen on the side, and it has a different structure to it. So that's basically just structural isomers, same molecular formula but different structure. Next we have stereoisomers. These are the ones we're gonna really speak about, and these have the same structural backbone but different orientations, so different arrangements and stuff like that. So there are two types. You have diastomers and you have enantiomers. Alright, so enantiomers are basically stereoisomers that are non-superimposable mirror images of each other. And in other words, these molecules are identical in every single way, and they have the same physical and the chemical properties. But you see how they're mirrored to each other. They cannot be superimposed onto each other. And then we have diastomers. So diastomers are stereoisomers that are not mirror image of each other's, as you can see here in the cis and the trans isomers, and they are not superimposable. So unlike enantiomers, diastomers have different physical and chemical properties such as melting point, boiling point, and solubility. So these two, unlike these two, with the cis and the trans isomers, these have different physical and chemical properties than the enantiomers. Alright, and basically these configurations have two or more stereogenic centers. So RRR configuration could turn into an RSR configuration depending on how it goes. That's why I said it's different than diastomers. Diastomers, basically all chiral centers must change. So for instance, if you have three R configurations, they must change to S configurations. We're going to discuss what the R and the S configurations are later. And one more thing about enantiomers, they are optically active, or they polarize in light. We got also conformers or rotamers. Right, you don't really need to know them that much, but here, so these are basically like, I would say, kind of like circular, cyclic, and these are basically behind each other, or like, I don't want to say on top of each other, but behind each other somewhat. And this is for instance called eclipse versus staggered. We're going to speak about them later. So I wanted to basically just describe what a superimpose meant with chiral objects and objects that have chiral centers. So it means that basically when you put them on top of each other, lay them on top of each other, they don't fit. They're like not the exact same image you have. Let's say, I don't know, you put a I don't know, a key in a mirror. Okay, that's a bad key. And then you get the reflection of this key. It's gonna be like this. And then when you put them on top of each other, you're gonna have one looking this way and one looking the other way. So they're not superimposed, they don't fit on top of each other. While achiral objects fit on top of each other. They're basically, the way they're built, they can be superimposed on top of each other. Next we have the configurations I was telling you all about. So basically staggered, this is staggered. It's like having distance between the top part and the bottom part, and it's more stable than eclipse because you see, usually atoms don't like sticking next to each other. Alright, if you go and check my chemistry video from bonding, like for instance, you got triangular planar, you got lone pairs, you got like the way these symmetries, it's like they try and stay away from each other as much as possible. So eclipsed interaction, you see how close it is? It's like causing a strain, the from the H and the H. But then you got the staggered, there is distance. There's 60 degrees here, for instance. It's like, oh, you're far away from me, I'm better now. And you have relative configurations. These describe the spatial position of the atoms relative to each other, and they used to describe enantiomers and diastereomers. And then you have absolute configuration, which we'll talk about. Describe the spatial arrangement of the atoms independent of other molecules. So now you need, let's say you get a molecule and you need to figure out the configuration for it. You need to figure out whether it's R or S configuration. So we're gonna start with the Kahn-Ingold prelog. You identify the center or the chiral carbon, the chiral center, which is connected to most groups, and then assign the priority of the atoms attached to the chiral center by looking at the atomic mass. The lowest, you rate the lowest, rotate the lowest to be in the back, the farthest back. So basically, in order to draw the lowest, it's like these dashes, and then most likely, in most cases, the hydrogen is in the back, is the lowest atomic mass, most likely. So now you're left with two more, and then in order to differentiate, you need to figure out the heaviest group. You attach the highest priority, then the second heaviest, you attach the number 2, and then the third heaviest, you attach the number 3. And then you circle, and then you, let's say, I don't know, you have this structure. Alright, just bear with me. And then you have here 1, 2, 3, and this is 4. So if you have this structure the way it's numbered here, and then you make a clockwise rotation, that's an R isomer. Alright, that's an R. But if you make it, if it's, for instance, if it was the other way, so here's 2, 3, alright, and then you go this way, that's an S isomer. Alright, if it's counterclockwise, it's an S isomer. And that's it for identifying configurations and isomers. And please don't forget to like, subscribe, share the videos, and let me know if you have any comments. Thank you so much.